Okay, so let's work this problem. We're going to try to find the maximum moment at I called it B, due to this. So here's our moving load. These are our wheel loads. And the way it was given is the total weight of the vehicle was 2,400 pounds, and it was 2 feet from the axle to the left and 1 foot on the side. Pretty small, almost like a little cart. And it's moving, it doesn't say which way it's moving, but from the diagram it looks like it's moving from left to right, so we'll assume that. The first thing we want to do is actually find what those contact forces are at the wheels. So it's not that hard. We can do a quick little equilibrium of the set. And I'll just call this reaction 1 and reaction 2. So if I were to sum the moments, about, say, R1, and make sure this whole thing is in equilibrium, what would I get? Well, I'd have the total weight of the system creating negative moment, so that would be 2,400 pounds at a distance of 2 feet, and then positive moment created by the reaction at 2 times its moment arm, which is 3 feet. So it looks like the reaction at 2 is 1,600? Does that sound right? No.
Yes.
Is that right? 1,600. And then I can sum forces in the y direction. I'll assume up is positive for my sign convention. And then I'll have that R1 and R2 are acting up, and then of course I'll have my 2,400 pound force acting down. So that looks like R1 is 800 pounds. So that shouldn't be too hard for you guys to get, but a little step just to get started. So as I move this vehicle across the structure, how many cases will I have to investigate? Any ideas? Well, we have 2 forces, so we have 2 cases. So the first thing I need to do is to find the influence line for the moment at B. So how do I do that? Well, Mueller-Breslau is going to tell me what? Well, we're going to go to B, and we're going to assume we have a hinge, right? That's really the inability to have moment. And then we're going to apply the moment. So how will point B move? Down or up? It'll probably move up. And then it'll allow the qualitative shape of our influence line to look like that. So now I can actually come over here and formally draw that the moment at B, the influence line will look something like this. I know the dimensions here are 15 feet and 15 feet. Now what I don't know is what's the value here. Also remember that when we do this, our units will come out in feet. So what do? What problem do I have to solve? What does this point on the influence line imply?
The maximum.
It is the maximum value, but it also tells you that on the original beam, which I'll draw here, where if I want that value, that means the influence line, the unit load is at that point. So if I solve this problem, I'll have the reaction at A, the reaction at C. If I solve for this problem for the moment at B, that will give me the value on this part of the curve. So how do I do that? Well, no matter where I cut the structure here, and work either the left side or the right side. I just need to know the reaction, right? Now, what's the reaction? Let's say I'm going to work the left side. What's the reaction if AY for this position? It's going to be a half. You can write an equation that will tell you that, but you can probably see that since the distances are equal, that AY is going to be equal to a half. So now I can actually cut the structure just to the left of this load, apply my 1/2. At 15 feet away, what do I have? I have the internal moment that I'm looking for, the moment at B. How can I find the moment at B? Oh, just to remind you, you would still also have a shear, but we're not looking for shear. We're just looking for moment. So how can I find moment? Well, just to make sure that you see it, if you sum the moments at the cut and set it equal to 0, what do you get? Well, this is, with my sign convention, this is a positive moment. The 1/2 would create negative moment with the moment arm of 15. So it looks like the moment at B is 15 divided by 2 feet. So now I know that this is 15 divided by 2. So now I have my influence line. So now I want to solve the problem. So what is the problem? Where does this cart, or what position does this cart on our structure will create the maximum moment at B? As I mentioned earlier, there's probably two cases. The first case, and also the vehicle is moving from left to right. So as it comes onto the structure, we're going to let R2 go to the maximum value first. So our case, we'll call it case 1. What I find it easier to do is to make a quick sketch of the influence line for the quantity we're looking at, the moment at B. And then I'll let my vehicle move from the left over, so the first reaction that will show up here is what? R2, and R2 is 1,600 pounds. And then 3 feet back will be the 800-pound force, and that's a total of 3 feet. And from our previous work, we know that this first triangular piece is 15, and the second one is 15. We also know that the height of our influence line is 15 over 2. So we know that value. We need to find out this value 3 feet back. So how do we do that? We can do similar triangles, right? I'll just do it that way as a difference compared to other ones. So the height of the triangle is 15 over 2, and that's to the length 15, as the thing we're looking for is to a length of what? 15 minus 3, or 12. So the thing that we're looking for is equal to what?
6.
It looks like 6, right? Everybody see that? So this value here would be 6. So now the maximum moment at B, I'll say for case 1, will be the 1,600-pound force times 15 over 2, and that's feet, plus the 800-pound force times 6 feet. So what's that equal to? Somebody help me out. And while you guys are calculating that, I'll go ahead and make some notes for the second case that we're going to work. Anybody get this value?
16,800 pound feet.
Anybody else get that? One head nodding. Anybody else?
16,800.
You got it too? How'd you get it? You were in this class before at this time and you remember this problem?
Yes.
Or are you seeing the future when you'll be back in the spring?
Well, this class is not for this spring.
What?
This class is not for this spring, is it?
Oh, yeah.
Oh, that's convenient.
That is convenient. So what's the answer again? 16,000 what?
800.
Okay, thank you. And that will be pound feet. So case 2, we'll redraw our influence line. And now we'll let the cart move farther to the right. So now the rear wheel, the 800-pound wheel, is at the top, and then 3 feet forward is the 1,600-pound force. So again, we need these values. We already know that the top is 15/2, and since the slopes are the same, 3 feet in front, this would also be 6. So now the maximum moment at B for case 2 would be our 1,600-pound force, but now it's times 6 feet, plus our 800-pound force times 15/2. I think you can see that this is going to be a smaller quantity. Anybody know the number?
15,600.
15,600? And that would be pound feet. So those are the two possible scenarios, but I think it's easy to see that that's the winner. So the moment at B max for this particular vehicle would be 16,800 pound feet. Anybody have any questions about that? I think that's a reasonable problem that you would expect on the exam, something like that. I don't think it would be inappropriate to have 3 forces, which would make you have check 3 cases. But I think this is, I think this is typical of what you would see on the exam. Maybe on the lucky side for you.
Lucky side.
Yeah, I think this is maybe one of the more doable problems. I probably would, on average, make it just a little more challenging, but not much. Conceptually, it's the same. Maybe another case, maybe shift this from the middle to the side so that you'd have to do a little more work finding the reaction, but after that, it would be pretty much the same. Any other questions? Okay.